am Dr. Zubair, Associate Professor from Maths Department, COMSATS Lahore. I welcome Professor Sheng, and he will continue his lecture in the last session over the metric spaces in our groups. Sir, please continue.
Thank you. Is this the really very last session already? I still want to apologize. I really wanted to be there in person. But it is my fault that I didn't notice during the COVID that my passport has expired. I mean, the application is taking so long. It's so far I haven't got a passport. This is very dangerous. And I would like not to use the full hour and brief through this unpublished work. This is a group of isometries, groups of isometries of these spaces which we have discussed in the third batch. And you saw already that the isometries are making the work more efficient. For example, you don't need to consider any 2 points, but one of the points can be the origin and the other one is in the positive. Other one has both coordinates non-negative. Using the isometry. And for those young colleagues who are finding papers getting rejected, let me tell you, the preceding papers are accepted within 1 week without change. And this paper has been, Yiming has submitted this paper, I think 4 times so far. And every time the rejection was very mild. We know that this paper cannot go to graph theory or combinatorics journals, so we started submitting it on something like group theory journals and things like that. And then they think it's graph theory. And the graphs, some combinatorics journals think it's group theory or geometry. So they politely reject. So he has submitted now to a journal which is now not rejected yet. The rejection comes very fast, which is good because they just say, sorry, it's a good paper, but it doesn't fit our journal's scope. Who decides the scope? I don't know, the managing editor. Okay, so this is not published yet. This was the basic work in Lei's PhD thesis. And as you saw already that it's being used, applied. Oh, this is not changed yet, I see. So this is the old version. So Lei actually, I asked, we each published 1 paper alone, and this I forgot. I think I have done page numbers, but this is an older version, and here this is in Questiones Mathematicae. This was, as we were talking in the preceding batch, preceding lecture, that our results work for n at least 2. And it doesn't depend on n, if n is at least 2. So what happens, the only thing which is happening is that n is smaller than 2. N is smaller than 2, if you have a dimension, then it is 1. So the dimension is 1, and for integers, so now we have only one set as a vertex set. And then we have a Cayley graph defined on the set of integers, ring of integers, and now the story becomes graph theory. Because as Professor Ion the metric dimension is a hard question. And this is not a finite graph, but it is still countably infinite, and the others are also countably infinite, but they happen to have a slightly more dimension, and it doesn't matter. When the dimension is higher, it's easier. This is what I felt when I was attending their seminars 15 years ago in Lahore. We walked back into mathematics and then forget about finite graphs. And then we can do something very beautiful and quickly publishable, deep, but not difficult. So, but then as soon as you step down into dimension 1 and considers all integers, then it's a problem. So that is where he published a paper considering only a few cases. If Professor Shabnam Malik is listening, she should see that this comment is very important. For finite graphs or countably infinite graphs, even for integers, things are very difficult. But if you slightly move into higher dimension, I think you can do a lot. Not at all, we finished everything we should do in those higher dimensions either. So he did some work, and these works are itemized below. For any generating set of the additive abelian group Z, the metric space of Cayley graph has metric dimension not exceeding 2 times the maximum element. This maximum is the linear order among integers. The largest element in the generating set S. And you have to really know that some young students might make a mistake. Generating set must consist of 1 and -1. No. The set is generating set for the ring of integers if and only if the greatest common divisor, the whole set is relatively prime. So it can be, for example, if you put 2, 3, 7, 11, that is a generating set for the ring of integers. Even if you put 11 and 12 and -11, -12, then it is a generating set. And it satisfies the 2 conditions. So this says that this gives an absolute upper bound on any space you can get from integers. This is no good, by the way. So, but he knows. But anyway, he published it anyway. And it was, this paper was accepted very quickly, without change. So the last groups of isometries is getting rejected because I think there people cannot understand the paper, even if it is easy, because it has spanned many different fields. And if you take all the continuous sets, generating set starting from -1 and to M, omitting 0, because 0 was omitted by the second condition, then its metric dimension is M plus 1. It's largest 1 plus 1, which means that bound is null. Also, and this is also true. This is a theorem he proved. He actually, when he first came, he proved this first. I insisted that he should start from dimension 1 first. And in our paper, this is the paper where I'm talking about. This is the unpublished paper, not yet. And it is somewhere, but I don't know, because he's the main author. He's submitting. I just receive messages from the journals. We obtain the following results. If A is a finitely generated additive abelian group, now here we are now not assuming that this group is torsion-free. As long as it is finitely generated abelian group, then it's fine. And let R be equal to, this R is a group. This is the group of order 2, cyclic group of order 2. 1 and with a reflection. Then, and we got here as all the translations. Then we have the following. Something is wrong here. Yes, for any finitely generated additive abelian group with the generating set satisfying the proper conditions, the maximum subgroup of the isometry, group of isometry of the space X is the group product of R times T. Some people, if they are reading this paper, probably they could have thought that these were all done when we were doing the orthogonal group of n-dimensional Euclidean space. When n is 2, then no, it is not the same, because this is our space is a subspace of the Euclidean plane, yes. but its group of isometry is not necessarily the one which is the orthogonal group. Of course, it is a discrete subgroup, yes. And then now we're determining this. And if you have a subgroup of this group product, this RT consists of R times T. Element R comes from R and element T comes from T. This is a general usual definition in group theory. If any set is a subgroup of this group, and if T is also a subgroup of the group T, or it is a subgroup of group of this, these two conditions are equivalent, and T dash is equal to this. T dash is the elements of T which are involutions. T is translation, so you don't regard it, the reflections are all in R. T translation, but T might have involution. The translation is in the reflection is in involution, but involution is not necessarily reflection, as you can see that, for example, in symmetric group, you have 1, 2, 3, 4, 5, 6, 7, 8. This product of these two cycles is an involution, but it is not a transposition. It's very easy, the basic example. And we proved that for vector groups over integers with, this is now in general, with unit vectors which has 2n elements, remember? So the degree, this is a locally finite metric space because degree is 2n at every vertex, regular degree n. The group of isometry is equal to the orthogonal group of Z over Z of, this is the orthogonal matrices, n by n matrices, whose entries are integers. And you know that such matrices exist, and it's very special, that matrix. You can actually write them all down. My group multiplied by the group, which is the vertex set itself. So this is a group product of the orthogonal group over Z of n by n orthogonal matrices. Orthogonal simply means that the inverse is transposition. and the Zn itself. Zn is a group. We proved this, and then this is I wanted to give idea of the elementary proofs of these results, but I don't want to bore you by going through the long and laborious details. The idea is very simple. You just have to, when we're trying to prove some group is a maximum subgroup, then you just prove that it's closed under the group operation, and then any group which contains this, which is a subgroup, also is equal to this one. This is maximum subgroup. And then when we're proving normal subgroup, we're simply using the condition of normal subgroup. So it's elementary. So we don't want to go through the really details. And they should really read our paper and examine it without really spending too much time on the details. The details are certainly correct. And we have observed this in the past lecture, preceding lecture. And we know that the isometries help consider things mathematically. We don't need to go through cases, case 1.1.1 until case 1.2.25. No, we don't want to write such paper. We apply the isometries first, and then we just consider one case. So we use this isometry to denote a group of isometries of X. And now here the basic result comes. The group of isometry for vector groups is isomorphic to the automorphism group of the graph. And its proof is not difficult. These two groups are identical. What is the proof? The proof idea is very simple. If it is an automorphism, if something is an automorphism of a graph of this infinite graph, then every two vertices, adjacent vertices are mapped to adjacent vertices, and non-adjacent vertices are mapped to non-adjacent vertices. So if you take two vertices at distance k, then each edge of that in this graph, and each edge of that is mapped to an edge. So that is the shortest path there with is length k. So the automorphism we have just taken is a member of the isometry. And if you take an isometry, it has to map points at distance 1 to itself. Therefore, it is an automorphism. So this is the proof. This is why I say it's elementary. This was known to many people earlier than this. If you have really considered graphs as metric spaces. Why is it looking so horrible? Something must be, okay, this is too much in detail. What I just said is this. We just got the operation is the composition of mappings. We just proved that every element of isom is element of odd. Every element of odd is an element of isom. That's enough. Because the binary operation is the same. Composition of mappings. In fact, we just have to prove that there's an injection from here to there, there's an injection from there to there, that's enough. Next is this here. We defined something called a sphere, which has something to do with bisectors. So sphere at center x with radius r is denoted by SXR. And isometry maps sphere to say sphere of the same diameter. The center is mapped to the center. This said this. So this is not difficult, you can see, but its proof is very much in detail. Isometry maps every geometric object to geometric object, same geometric object. So it maps sphere to sphere. But you need to write it rigorously down, and this has no mistake here. I'm sure about it, and they should really not fail to understand our paper and then reject politely. They should really accept politely. Okay, I'm just joking, don't worry. So now here is a finitely generated additive abelian group. We're not assuming that torsion free at the moment. And S is a finite generating set because it's finitely generated. So there must be a finite generating set satisfying the natural conditions. And this is the space. And rho is a bijective mapping, which maps every vector to its negative vector. Then this mapping must fix the origin. Is it difficult? I don't think it's difficult to understand. Maybe they're thinking our paper is just trivial, but that is probably understandable. Anything that maps a vector to its negative must fix the origin, isn't it? Oh, that's what the proof is here. So it is essentially reflection at the origin. So the origin is mapped to itself. And this is called the reflection, naturally. Therefore, reflection is in an involution. That is said by this identity here. And denote this group of order 2, cyclic group of order 2, which contains 0 and 1. 0 is 1 and 1 is rho. Then it is a subgroup of ISM, which is very easy because reflection preserves distance. Translation is defined in this way. T sub A is every vector plus fixed vector A. And we put all the translation in here. This is actually a affine group. Then translation is a subset of the isometry. And translation in this kind of Euclidean, or not Euclidean, but where the graph theorists call it Manhattan. can translation change distances? Yes, it will change distances in New York, but no, not in mathematics. So it's a subset, and then after that, we prove that it's a subgroup. See, there. First, it's a subset, then it's a subgroup. And then now prove that this group product of these two groups is a subgroup of the isometries. Not difficult. Just go through the subgroup verification. There's something missing here again. Oh, I see. The missing condition I was looking is origin is fixed. If any isometry fixes the origin, then it is reflection. That's what this lemma says. If any isometry of this space fixes the origin, then it is the reflection. So now, here, if you compare this with the orthogonal group of the Euclidean plane, for example, in the orthogonal group of the Euclidean plane, every rotation around the origin fixes the origin, but some rotation is not a reflection. So here the difference is coming within our discrete subgroup. So if any isometry fixes the origin, then we prove that it is a reflection. Wait a minute. Yeah, if any isometry fixes the origin, then it's a reflection. This is certainly, there's no mistake here. And if any student, I gave this paper to some of his colleagues to read, and they struggled through this 6 months, and it is actually unworthy, because you should really understand that we are proving just any isometry that fixes the origin is a reflection. That's what is in here in this detailed proofs. And then, now if G is a subgroup, if G contains RT as a subgroup, RT are given already, then G is a subgroup of the isometry. Also, then G is equal to RT. So we prove that the RT is maximum subgroup, maximal subgroup. See, it happens that if you have done the preparation, this important theorem is now proof is easier. Then we look at that T dash we defined. We characterized all normal subgroups of RT. RT being the maximal subgroup. So we need to just consider, then R is a normal subgroup. Identity element alone is a normal subgroup. And then other normal subgroups we'll just have to consider the normal subgroup of RT. So this is a necessary and sufficient condition for any subgroup to be normal. Why don't they publish our paper? It's actually a beautiful paper, by the way. I told my student, this work is ground, but it is beautiful. It's not difficult. We know it's not difficult. Then why do mathematicians prefer only difficulty and give up beauty? I prefer beautiful papers first. Difficult papers I reject when I referee. That's the opposite. I only look at beauty of mathematical papers. This is beautiful because we are just doing elementary verification according to the definition, and we characterize all normal subgroups for this group of isometries. And I'm getting 42, so I should stop here. We did more here. So I'll just scan through it. We did more. For example, isometries are linear mappings when we define linear mappings, because these are vector groups, so we have linear mappings. Only that they are not vector space, it's vector groups. Isometries are linear mappings, and we did orthogonal group. We actually know exactly what these matrices are like, as we said here. 1 or negative ones, entries are 1 or negative ones, and then you can actually enumerate all of them, but we didn't go that way. We should publish this paper. And then we worked out precise group of isometries for our space. This was announced earlier. This is one of the main results. It is a group product of the orthogonal group over integers and the n-fold Cartesian product of integers itself. And you see that the automorphism group of these graphs are larger than the vertex set. Order is larger than order of the graph, because every isometry is an automorphism. This means also that these spaces are highly symmetric. Group acting on them is large. Not too large, but slightly larger. So this is all we did in this paper, and thank you very much for entertaining, or no, so for being maybe entertained or bored. And thanks the organizer and Professor Sana Javed for asking me more than 3 years ago, and apologize that I wasn't there. Thank you very much, everyone.